Hello, welcome back to Larry's Classroom. Today we're going to continue our discussion of series circuits, and we're going to start by talking a little bit about the polarity of IR voltage drops. And of course I times R is equal to voltage, so we often call a voltage drop an IR drop. I'm going to draw two simple circuits here, very similar. We're going to call this R1, and we'll call this V1, which is appears across this resistor. And we're going to draw an arrow this way indicating electron flow. So we see here electrons, being negatively charged particles, are repelled by the negative terminal of the source, go through whatever the load is. In this case the load is R1, and return to the positive terminal source. We also see though that the voltage, polarity of the voltage across R1 is the electron flows into the negative terminal of the load and out of the positive terminal of the load. And considering this wire from the top of R1 to our voltage source has basically essentially zero resistance, this polarity here is going to be the same at this point. I'll call this point A as at point B. And the same token on the other side here. At the lower end of resistor R1 we have a positive terminal, and basically the same thing. The wire going back to the source has essentially no resistance, so the voltage drop across that wire is essentially zero. So the polarity at the bottom of R1 is the same as here, and we'll call that point C and point D. We have similar polarities, but what we notice here is that these polarity of potential difference across R1 is going to be causing the electrons that are in R1 to be repelled towards the bottom and attracted by the positive charge. So our polarity of our voltage drop related to electron flow is the electron flow goes into the negative terminal, out of the positive terminal of the positive polarity. Electron flow, I'm going to put load because it's opposite in a source, into negative terminal, out of the positive terminal. Now we're going to draw a very similar drawing. We're going to talk about related to conventional current flow. Put the same polarities of our source here, negative, positive. The same polarities on our same resistor R1, plus, minus. And our voltage 1 appears across the resistor. We call it IR drop or voltage drop, which voltage always appears across some component between 2 points. You can't get a voltage to appear across a single point because you can't have a potential difference at one point. You have to have 2 points and you have to have a potential difference. Now we're going to talk about conventional current flow. Current flow. And as we talked about before, conventional current flow flows from positive to negative. We got the same polarities across our resistors as before for the same reasons, but conventional flow is the flow of positive charges. So inside the resistor, any positive charges will get repelled by this positive terminal at the bottom and attracted by the negative terminal. positive charges are repelled by the positive terminal of the source and attracted by the negative terminal source. So when we say conventional current flow, and we'll say in the load, just like we did before, goes from into the positive terminal and out of the negative terminal. Now the important thing that really these two diagrams, which are very, very similar, illustrate is whether you think in terms of electron flow or in terms of conventional current flow, you have the same polarities appear across your loads. So analysis, when you analyze a circuit, it doesn't really matter whether you use conventional current flow or electron flow. The results will be the same in the end. The polarities will be the same. The amperage values will be the same. The direction of the amperage flow, the current flow, will be opposite, but that's kind of what we already know, is that electron flow is opposite in direction to conventional current flow. Very quickly think about a wire. We've talked about these a little bit before, but we're going to very quickly think about a wire, and of course our current carriers, which are negatively charged, are electrons. I'm going to draw a bunch of little electrons in here, negatively charged. And if we put a negative voltage on here and a positive voltage on here, we will have electrons flowing this way. We will have negative charges moving from right to left. Right to left. Well, what is a positive charge? In a lot of ways, it's just a lack of a negative charge. So if we got negative charges going in this direction and causing what happens is, as the negative charges move this way, this end becomes more positive. So we really do have an equal number of positive charge, equal amount, let's say an equal amount of positive charge moving in the opposite direction of the negative charge. In something such as a wire, this positive charge is not attached to a physical charge carrier that can move, where the negative charge is attached to an electron which actually can move. The positive charge ends up being the molecules, the atoms of the conductor that have missing electrons. But the rate of flow of negative charge right to left will be equal to the rate of flow of positive charge. Let's see, we got our negative charge flowing from left to right here. Let's get that correct. Got our negative charge in this case flowing from left to right. Which is being carried by the electrons, where the positive charge is happening because electrons are leaving. So the positive charge is moving right to left, at the same rate that the negative charge is moving left to right. And we also noticed in our drawing just a few minutes ago that this, whether you think in terms of conventional current flow and positive charge, or electron flow and negative charge, your polarities across all your components in your circuit end up being the same. Now we're going to talk a little more about these polarities. We'll draw another circuit. And we're going to mostly think about this in just terms of electron flow at this point, which we'll use most of the time in this course. VT, we really don't care what the value of it is for this demonstration. The polarity is negative and positive. We got two resistors over here. We'll call this R1. We'll call this one R2. I'm going to label some points here. I'm going to call this point A. I'll call this point B. And this point here we're going to call point C, and just below it point D, which are the bottom and top end of this resistor. There's a little wire in between them, connecting them together. We'll call this point point E, and this point point F. And we're thinking in terms of electron flow. So we're going to say I. We're not going to worry about the value because we're thinking more polarities rather than values. And electron flow is flowing that way from negative to positive. Across R1, what we see is the electrons flow into the negative relative polarity terminal of R1, as we just saw in our diagram a few minutes ago. And they come out of the positive end. So basically, point B is negative with respect to point C. Continuing around the loop here, when we look at R1, electrons flow into point D, which is negative with respect to point E, which is on the positive end of R2. Kind of the most interesting thing here is C and D are both the same point, yet we have C labeled positive and D labeled negative. And that's basically because C is positive with respect to point D, and D is negative with respect to point E. Another way to think about that, as we travel around this circuit, if we were to connect our voltmeter right here, let's just draw a terminal, and this is going to go to a voltmeter. I'm just going to put I'm going to put VM that indicates voltmeter, and we have another terminal. If we connect that terminal to right here, we'll see that this point A is negative with respect to point F, which is the result of the polarity potential difference of the source. If we disconnect from there and we move to over here to point C, we will see that we have become less negative. We're taking our voltage measurement a little further from the negative source of the power supply, but a little closer to the positive source of the power supply. So that's basically what we saw across the voltage drop of R1. We became a little more positive as we went across it, or a little less negative, depending on how you want to look at it. And as we move to the next, if we move our meter to the next point, E, connect there, the same things happen. As we get closer and closer to the positive terminal, we become more positive and less negative. So that's kind of a demonstration of how the polarities of the voltage drops work, and that's why we see this positive and negative both kind of at this point. But this is related to, we got more positive from the supply. Here we got more positive. We got closer and closer to the positive end, or further and further from the negative end. If we went around the circuit the other direction with our meter, we would start here with very little, and as we moved, just taking readings, as we moved up to here, we would see it become a little more negative, a little less positive, a little less negative. Go up here, a little, even more negative, and even a little bit less positive. And basically, the other thing you can see here is these polarities pretty well match up with the polarities of the source. The negative end of R2 is closer to the negative end of the source than it is to the positive end of the source. The positive end of R1 is closer to the positive end of the source than it is to the negative end of the source. And by the same token, the positive end of R2 is closer to the positive end of the source than it is to the negative end of the source. The negative end of R1 closer to the negative end of the source than it is to the positive end of the source. So this is kind of how the polarities of the voltage drops. And I'm going to quickly draw that back up here. And the voltage drop is basically how much voltage appears across that resistor. The voltage drops, becomes less. The value here, right here, is dropped from this value by the amount that's dropped across here. Same thing here on R2. The voltage from this point to this point is dropped. It's that much less than the voltage here. If you look from here and you look across from the top of R1 to the bottom of R2, the total voltage drop, the sum of those two voltage drops, is that much less than the supply voltage. So that's why we call it a drop. It's like that voltage appears there, there's less voltage left to appear on the rest of the circuit as you move your way around. I think that's a good way of describing it. We're going to talk a little bit about how total power divides up in a series circuit. We're going to draw another little circuit, talk about power. And we're going to put 100 volts on this supply, negative, positive. We're going to draw a couple resistors. We'll call these R1 equal to 30 ohms, R2 equal to 20 ohms. The first thing we want to know is how much is the current in the circuit. And you probably recall that we have RT, R total, equals R1 plus R2. For however many we have, in this case we only have 2, so that's going to be 30 ohms plus 20. I'll write that underneath. 30 ohms plus 20 ohms, and that is going to equal 50 ohms. So we have 50 ohms total in the circuit. We have a 100 volt supply, so we can say that our current is equal to ohms by Ohm's law, voltage divided by resistance, 100 volts as we have here, and 50 ohms as we're showing here, divided by 50 ohms. That gives us 2 amps of current flow. And we're talking electron flow, negative, positive, so we're going to draw us a little loop this way, and we're going to say I, current, intensity, equals 2 amps. So we're going to look at the power. Let's calculate the voltage across each resistor. Well, let's calculate the voltage across each resistor. We have 2 amps. We have voltage equals I squared R. Oh, I squared times R. And you might sometimes this referred to as IR loss, which is talking about how much voltage gets dropped, or that's power. That's power. I want power. Darn it. Power equals. I want to calculate power. Power equals I squared R. That's where the I squared R loss comes in. If you got a cord feeding some utilization equipment, maybe a vacuum cleaner that's 100 feet away, that cord does not have zero resistance. And there is current flow to drive that vacuum cleaner. So the current flow times the resistance, current flow squared, determines how much power is lost in that cord. And that's why we call it sometimes I squared R loss. But we're going to think about how much power is dissipated by R1. So we say P R1 is equal to, well, 2 amps occurs everywhere in the circuit, so it's 2 squared times 30 ohms. So we got 4 times 30 equals 120 watts. So we have power here equal to 120 watts, and that is being dissipated as heat by R1. It would need a pretty substantially large resistor to do that without failing. Let's think about the voltage that appears across that particular resistor. We're going to do voltage equals I times R, and that's where we talk about voltage drop. 2 amps times 30 ohms equals 60 volts. So we got a voltage equal to 60 volts here. We're going to call this power 1, voltage 1. I'm just going to call this power 1 instead of power R1. Power 1. So we're going to do the same calculations for this second resistor. We're working on learning more about calculating series circuits and understanding how the power divides up and such. So we're going to think about resistor R1 now. We're going to go power 1, or power 2, we're thinking about resistor R2, we're going to use the same R squared R formula, the same 2 amps, so we've got 2 squared, and we're going to multiply that times the value, the resistance of R2, which is 20 ohms, times 20, that becomes 4 times 20 equals 80 watts. So we have a power 2 of 80 watts, which is basically, that is the amount of heat that R2 will be creating, will require to dissipate into the air. And as you can see again, that's going to be a substantially physically large resistor to dissipate that much heat without burning up. We're going to calculate the voltage on that particular resistor. And we're going to use the same formula, V equals IR, V equals IR. And we're going to say the current, same in the loop everywhere. You can't have 2 different currents in a loop. You can't have 2 amps here and 3 amps there. And that's going to be 2 squared times, oh yeah, no, it's not squared, it's IR. 2 times 20, and that gives us 40 volts. So we have voltage 2 equal to 40 volts. We've talked before, voltage total equals voltage 1 plus voltage 2 on however many we have. Here we only have 2. Voltage total equals voltage 1, which is 60 volts, plus voltage 2, which is 40 volts. So that 60 and 40, 100 volts, which you see is equal to what our supply voltage was. So sometimes we talk about these voltage drops, IR. We will say that the voltage drops are equal in sum to the voltage sources. We have 100 volts here. We have a voltage drop of 60 plus a voltage drop of 40. That's 100 volts of voltage drop. It's equal to our voltage sources that we have in this particular circuit. And of course our polarities, like we talked about before, plus, minus, plus. Now, what's our total power? We use the total resistance to come up with total amperage. We know the power source, and so power is equal to current times voltage. That's from our power formulas. And what we have here are 2 amps times 100 volts, and that equals 200 watts. And we have our power formula that says power total equals power 1. Power 1 plus power 2 plus power 3 dot 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 on up to power n, however many we have. In this case we only have 2, so I'm going to erase this part of it. So what's our power 1? We calculated that here, and we came up with 120 watts. And what's our power 2? We calculated 80 watts. And what we have here is 120 watts plus 80 watts equals 200 watts. So we found that by calculating the power being supplied by the load, or by the source, the 2 amps at 100 volts, shows 200 watts of power supplied. And we looked at the power being dissipated by the 2 resistors, and we found that we have 200 watts of power consumed. So you'll find this to be true too. Power supplied is going to equal power consumed. Any power supplied by this is going to be used up somewhere, and this circuit is being used up as heat. In a radio transmitter, it might be being converted to an electromagnetic wave and radiated through space for other radio receivers to pick up and find the information on, but the power supplied will be equal to the power consumed, and this simply is just heat that we've got going on here. So we kind of learned about the total power series circuit, and we found that power total is equal to power 1 plus power 2 dot 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 up to power n, for however many you might have, with n being the number of power consumers you have. And this, you see, this is kind of similar to the voltage summation that we had. Voltage total was, well, this is what we're talking about, a series loop. Voltage 1 plus voltage 2 up to voltage n. So the power supplied, this is, we'll call this is the source side, and this is related to series circuit. Though this power formula is pretty much good in any type of circuit, but we're talking about series circuits. And this is basically our load side, load portion of the circuit. We'll just call it load. Take the word side out of there. But we see here a lot of similarity between this voltage total formula and the power total formula. The power total supplied by the source is the sum of the power consumed by all the components of the load. And on a series loop, the voltage total supplied by the source is going to be equal to the sum of the voltage drops across each component. And the voltage drop would be what you would read across that component if you put your voltmeter directly across it. So we're going to draw another circuit here, and we're going to talk about, let's see here, draw the circuit here. We got two power sources in series here. And here we have a 6-volt supply with a negative polarity terminal here and the positive terminal here. We have a 4-volt supply in series with it with a negative terminal of it there and the positive terminal of it there. And we're going to have a resistor here for a load. And then we're going to say this is a 2 ohm resistor. There's more than one way we can calculate this. We're interested in finding the current. We have a total. We add these two voltages together. You notice the polarities are plus to minus. They're what you call series aiding. If we start at the bottom here, we would get 6-volt negative. We go across up to the second supply, we got 4 volts more negative, so we get to a 10-volt level. I equals V over T, and that's basically 10 volts divided by 2 ohms, so we have 5 amps. So we have calculated the current by summing the voltages that were series aiding to a total voltage, divided that by the total resistance, which we only have a single resistor here, and come up with amps. There's a couple other little bit different ways to look at this. We could look at each of these loads separately. Let's start by just taking the 4 ohm or the 4 volt load supply out of there. Now we only have 6 volts. So if we calculate the current now with 6 volts supply, we have I equals voltage divided by, this is R here, resistance, I call it total, but voltage divided by total resistance, I shouldn't have put a T there. I equals voltage divided by resistance equals 6 volts divided by 2 ohms. And now we have 3 amps. So we'll change that. We have 3 amps now if we have just the 6-volt supply in the circuit. And I'm going to draw the resistor alone over here, 2 ohms. In the case of the 6-volt supply, we would have 3 amps. And the direction is again counterclockwise from negative to positive. Now we're going to change things a little bit. We're going to imagine if we only had the 4-volt supply in there. 4 volts. So we have now, instead of the 6 volts or the 10 volts that we had, we have the total of 4 volts. Now if we work with the 4-volt supply, again, same formula, I, current, or intensity, equals voltage divided by resistance, we now have 4 volts, and we divide that by the same 2 ohms. We have 2 amps. So, and you know, the polarities are such, it's the same direction as before. So we'll draw that arrow to match that. And I'm going to draw our 2 ohm resistor right here. 2 ohm. And we're going to put a current arrow, which is now 2 amps. And what you may notice, before when we had 10 volts, the 2 supplies both in there at once, we ended up with 5 amps. When we put the 6 volt supply, we got 3 amps. We took the 6 volt out, we replaced it with just the 4 volt and analyzed the circuit with the 4 volts alone. We have 2 amps, but you may notice that 3 amps plus 2 amps equals 5 amps. So I'm going to draw a couple arrows. I'm going to draw the 2. It was in the same direction. We're going to do 2 amp supply, or 2 amp current flow. And another arrow. And this has 3 amps from the other circuit. And we're going to erase this stuff here. But as I said, the 2 amp plus the 3 amp added to 5 amps. The 2 amp came from 4 volt supply. The 4 volt supply provided the 2 amps. The 6 volt supply divided the 3 amps. And you notice that 6 plus 4 equal the original 10. 2 plus 3 equal the original 5. They're both in the same direction. And this is a valid way of analyzing things. We basically call this superposition. So you can often analyze a network of resistors by looking at what happens, all the currents and voltages provided by all the currents anyway, provided by one power supply without the other power supply, and then all the currents provided by the second power supply without the first power supply, and adding them up like this. And these are aiding. In the case, well, we'll do one of those in a minute. In the case they're different directions, it works out differently. But we had both of our polarities the same, so they added up the same. And superposition can be a handy technique for analyzing circuits at times. We're going to draw another circuit up here. Similar, it's going to have a 4 volt supply. 4 volt. Negative, positive. And it's going to have a 6 volt supply. But you notice in this case, the polarity of the 6 volt supply is opposite of the polarity of the 4 volt supply. We'll put the same 2 ohm resistor in here. There's a couple ways you could look at that. Before, these were the same direction, so they added up directly. But in this case, if we started with our voltmeter here and went to here, we would read plus 6 volts. We go to the next one, we would have went down, we would have become negative 6 volts relative to this point, or negative 4 volts relative to this point. So from positive 6 volts, we went down 4 volts to positive 2 volts. So that ends up being positive 2 volts. being this one was opposite in polarity, it kind of subtracted from this one. And we end up with the polarity of the larger supply. If this had been opposite in value, same polarities but opposite, we would have had the 2 volt here and the 6 volt here. We would have started here, we would have read plus 2 volts. I don't think I calculated this right. I think this should have been plus 4 volts. No, plus 2 volts. Oh, this is 6. That's what's wrong here. Yeah, this is 4. I mean, that's so my original plus 4 was good. Yeah. But now that we've changed the polarities, we start here. If we read our voltmeter, we get plus 4 volts. But now we become 6 volts more negative. So we end up with, oh, that was plus 2, darn it. Plus 2. Yeah, originally we had plus 2. But now we start with, if we read our voltmeter here, and we read here, we have plus 4 volts. And we read from here to here, we go down 6 more volts, so we end up with negative 6 volts. So what we saw again is the total voltage is the largest one minus the smallest one, but the polarity matches the largest one. But I'm going to go back to my original circuit here. We had 4 volts here, 6 volts here. Plus 6, down 4 to 2. I think I wrote that wrong. Went to negative 2, not to positive 2. When we had them reversed, it went to negative 2. But these are series opposing, so that the voltage don't add up directly like before. It's a little less than the largest one by however much the smallest one is, and the polarity matches the largest one. With this plus 2 volts, we got I equals V over R, 2 volts over 2 ohms, 1 amp. So, but now we're gonna do electron flow, and you notice it was positive here, so the electron flow, I of 1 amp, flows in that direction. Now we're going to do this one using the superposition method too, real quickly. We have just the 4 volt, supply. Now we have a negative 4 volts. So we have I equals 4 volts divided by 2 ohms. This equals 2 amps. And being it's negative to positive, we have current this way. So we're going to remember this, we're going to draw the little resistor, 2 ohm, and we're going to draw 2 amp arrow to indicate that with the 4 volt alone, the current is in the downward direction in this particular drawing. Now we're going to change this over. We're going to put that 6 volt supply in there, which had opposite polarity. Six volt, negative, positive. So we're going to, now again, we're going to use the V over R. Our voltage is 6 volts. Our amperage is 2 ohms. Our resistance is 2 ohms. So we have 3 amps. Now what direction is this flowing? Well, I of 3 amps is flowing in the opposite direction now. So we can draw our 2 ohm resistor like this, 2 ohm. But now our current is flowing, our electron flow is in the upward direction on this drawing. So we have 3 amps going this direction. And let's look at how that adds up using superposition. If we have the resistor alone over here, and we have 2 amps in the downward position and direction, 2 amps downward, and we have 3 amps upward, well, we again subtract the 3 minus the 2 and use the direction of the larger one, so that ends up being 1 amp in the upward direction. And if you'll recall our original circuit, we had the 4 volt, and we had the 6 volt, and this was negative, positive, and this was positive, negative, which led to a plus 2 volts here, and the 2 volts divided by 2 ohms gave us 2 amps. And the lower side of this combined power supply was most negative, so we had our current this way. That's 1 amp, excuse me, 1 amp. We have 1 amp, so we ended up with 1 amp intensity I current equals 1 amp in the upwards direction, which was the same thing we got when we solved this particular problem using superposition. So superposition is a valuable analysis technique, not necessary for simple circuits as this, but when you have multiple branches and 7 or 8 resistors, three branches and 3 power supplies, sometimes superposition can be the easiest way to solve a network. In this case, it's typically easier just to solve for the voltage and do it like any of the series circuits we've been doing. Anyway, I think we'll call that good for now. Remember to like and subscribe. And until the next time, keep on learning.